Transformers are widely used in all branches of electronics. A transformer is defined as a passive electrical device that transfers electrical energy from one circuit to another through the process of electromagnetic induction. Transformer is most commonly used to increase or decrease voltage levels between circuits. In today's video, we are going to cover the basics of transformers working and some types of transformers. A basic transformer consists of two windings. These are known as the primary and the secondary. In essence, power enters on the primary and leaves on the secondary. Some transformers have more windings, but the basis of operation is still the same. The working principle of a transformer is very simple. Mutual induction between two or more windings, also known as coils, allows for electrical energy to be transferred between circuits. Also, the transformer provides DC isolation between the input line and the output. It also performs a voltage step up or step down function for the supply. If the transformer is improperly designed, it would adversely affect the supply operation and the reliability of the semiconductors which we used in the circuits. All types of electrical transformers used in electronic circuits basically consist of two inductors. One of these inductors is meant for supplying alternate current from an external source and is referred as primary winding. The other coil in the primary winding induces the voltage is known as secondary winding. If two coils are placed near each other, the change in flux in one coil will cut the turns of the other coil and will induce a voltage in it. Then these two coils are said to have a mutual inductance. In the previous video, we already discussed about mutual inductance. Types of electrical transformers. Power supply transformer. It's available in two types. Step down transformer that decreases the AC voltage and step up transformer that increases the AC voltage. The AC output frequency from a transformer is always the same as the AC input frequency. Some types of electrical transformers are audio frequency transformer, radio frequency transformer, intermediate frequency transformer, auto transformer, isolation transformer, driver transformer, pulse transformer, etc. First, we are discussing about power transformer. One of the important and commonly used transformer is power transformer. It is very widely used for stepping up and stepping down the voltage at the electrical power generating station and distribution station. For example, consider this diagram. Here, power transformer is used two times while delivering electrical power to a consumer who is far away from the generating station. First time is at a power generating station to step up the voltage generated by the wind generator, and in the second time it is a distribution station to step down the voltage received at the end of the transmission line. Power transformer working principle. Power transformer works on the principle of Faraday's law of electromagnetic induction. It is the basic law of electromagnetism which explains the working principle of inductors, motors, generators, and electrical transformers. The law states, when a closed loop or shorted conductor brought near a varying magnetic field, then the current flow is generated in that closed loop. In order to understand the law better, let us discuss in more detail. First, let's consider this scenario. Consider a permanent magnet and a conductor is brought near to each other first. Then the conductor is short circuited at both ends using a wire, as you can see here. In this case, there will be no current flow in the conductor or the loop because the magnetic field cutting the loop is stationary and as mentioned in the law. Only a varying or changing magnetic field can force current into the loop. So in the first case of the stationary magnetic field, there will be zero flow in the conductor loop. Now consider if the magnet is moving back and forth like a pendulum, then the magnetic field cutting the loop keeps changing. Since there is a varying magnetic field present in that case, Faraday's law will come to play and thereby we can see a current flow in the conductor loop. As you can see the image, after the magnet moves back and forth, we get to see a current flowing through the conductor and the closed loop. Now let's remove the permanent battery to replace it with other varying magnetic field source like this. Now an alternating voltage source and a conductor are used to generate a varying magnetic field. After the conductor loop brought near to the magnetic field range, then we can see an EMF generated across the conductor. Because of this induced EMF, we will have a current flow. The magnitude of induced voltage is proportional to field strength experienced by the second loop. So, the higher the magnetic field strength, the higher the current flow in that closed loop. Although it is possible to use a single conductor setup to understand Faraday's law, but for better practical performance, using a coil on both sides is preferred. Here, an alternating current is flowing through the primary coil 1, which generates the varying magnetic field around the conductor coils. And when the coil 2 enters in the range of the magnetic field generated by the coil 1, then an EMF voltage is generated across coil 2 because of Faraday's law of electromagnetic induction. And because of that voltage in coil 2, a current flows through the secondary closed circuit. Now you have to remember that both coils are suspended in the air. So the medium of conduction used by the magnetic field is air, and the air has higher resistance compared to metals in the case of magnetic field conduction. So if we use a metal or ferrite core to act as a medium for electromagnetic field, then we can experience electromagnetic induction more thoroughly. So now let us replace the air medium with the iron medium for further understanding. As shown in the figure, we can use iron or ferrite core to reduce the magnetic flux loss during power transmission from one coil to another coil. During this time, the magnetic flux leaked into the atmosphere will be considerably less than the time we used air medium, as a core is a very good inductor of the magnetic field. Once the field is generated by coil 1, it will flow through the iron core reaching the coil 2, and because of Faraday's law, coil 2 generates an EMF which will be read by the galvanometer connected across coil 2. Now if you observe carefully, you will find this setup similar to a single phase transformer. And yes, every transformer present today works on the same principle. Application of power transformer. The power transformer is mainly used in electric power generation and at distribution stations. It is also used in isolation transformers, earthing transformers, 6 pulse and 12 pulse rectifier transformers, solar PV farm transformers, wind farm transformers, etc. It is used for reducing power losses during electric power transmission. It is used for high voltage step up and high voltage step down. IFT or intermediate frequency transformer. Intermediate frequency lies between the audio frequency and radio frequency range. The audio tone is compression waves traveling through air that your ears can pick up. The RF signal is waves in the electromagnetic field that your ears have no way of picking up. IFTs are meant to be operate at a fixed frequency known as intermediate frequency. IF transformers filter frequencies using the principle of resonance. As we have learned, when a signal runs through a capacitor and coil, the circuit tunes to the resonant frequency. IF transformers are tuned to resonate with the IF frequency of 455 kHz. The standard IF in radio reception is 455 kHz. IFT is designed to respond to this frequency only. This achieved by using parallel capacitors across primary and secondary windings. The assembly of IFT enclosed in an aluminum can includes a capacitance of 40 picofarad and an inductance of 3 millihenry. Different frequencies are fed to the primary winding and the primary capacitor. The circuit resonates with the IF frequency and non-resonant frequencies are minimized. The IF signal on the primary winding creates a magnetic field that picked up by the secondary. So now the IF signal on the primary is also on the secondary. As we have learned, the coils in the transformers are magnetically coupled but electrically isolated. We also learned that the arrangement allows voltage transformation. Transformers change voltage by changing the number of windings in the coil. If the secondary has the same number of windings as the primary, the voltage remains the same. If the secondary has fewer windings, voltage is reduced. And if the secondary has more windings, voltage is increased. This is usually the case with IF transformers to help boost the signal. Voltage transformation and isolation are important characteristics of all transformers, no matter how big or small. Why intermediate frequency transformers are used? Intermediate frequency transformers are used for three general reasons. Number one is, at very high frequencies, signal processing circuitry performs poorly. Active devices such as transistors cannot deliver much amplification. Ordinary circuits using capacitors and inductor must be replaced with complicated high frequency techniques such as strip lines and waveguides. So a high frequency signal is converted to a lower intermediate frequency for more convenient processing. For example, in satellite dishes, the microwave downlink signal received by the dish is converted to a much lower IF at the dish to allow a relatively inexpensive coaxial cable to carry the signal to the receiver inside the building. Bringing the signal in at the original microwave frequency would require an expensive waveguide. The second reason is in receivers that can be tuned to different frequencies is to convert the various different frequencies of the stations to a common frequency for processing. It is difficult to build multi-stage amplifiers, filters and detectors that can have all stage track in tuning different frequencies. But it is comparatively easy to build a tunable oscillator. And the main reason for using an intermediate frequency is to improve frequency selectivity. In communication circuits, a very common task is to separate out or extract signals or components of a signal that are close together in frequency. This is called filtering. Example is picking up a radio station among several that are close in the frequency range. Application: IFT transformers are also used in the intercarrier TV receiver sound section of television. Perhaps the most commonly used intermediate frequency for broadcast receivers are around 455 kHz for amplitude modulation, that is AM receivers, and 10.7 MHz for FM receivers. Next one is pulse transformer. The transformer which handles voltages and currents in the form of pulse are called pulse transformer. Pulse transformer is mostly used in power electronic circuits as an isolating transformer to isolate source and load. It is also used in television, radar, digital computers, etc. The main function of the pulse transformer is for changing the amplitude of voltage pulse, for inverting the polarity of the pulse, for coupling different stages of pulse amplifiers, for an isolation transformer, etc. It shall be noted here that the turn ratio of an isolation transformer is 1:1. The input voltage to a pulse transformer is of discontinued type as shown in this image. The most and basic requirement of such transformer is that it should reproduce input voltage at its primary to secondary as accurately as possible. The image shows that the square input voltage pulse at the input terminals, the pulse width varies from fraction of microseconds to 25 microseconds. Normally enough time lapse before the next pulse arriving at the input terminals. The waveform of output voltage can be determined by using the equivalent circuit of the pulse transformer. A typical output voltage waveform is shown in this image. In this image, the pulse parameters are also shown and it must be noted. Rise time: here the time interval required for the output to rise from 0.1 to 0.9 of its final value. The transformer response to the flat top portion of the input voltage pulse can be determined using low frequency equivalent circuit. The output voltage seems to have a downward tilt or drop off during pulse duration time. The output voltage cannot be flat as this would mean that DC is flowing through transformer, which is not possible. The drop of the output voltage pulse can be minimized by using high magnetizing inductance for the transformer. Again, when the input pulse is 0, the output pulse does not reduce to 0 instantaneously because of magnetic energy stored in the inductance of the transformer. Rather, there is some definite Hall decay time to reach the output voltage pulse to 0 value. Pulse transformers are quite small in size. To minimize the leakage inductance, there are few turns of primary and secondary, but to have minimum magnetizing reactance. Its core is either made of ferrite or highly permeable alloys like permalloy. Audio frequency transformer or AF transformer. Audio transformers use the isolation property and creates isolation between the output speakers or audio circuitry with the transformer's input side amplifier system. In such case, the primary and secondary windings turns ratio fixed to 1:1. Due to this, the transformer does not alter the voltage or current level. It does only create isolation between the input amplifiers with the output speaker system. Other than the isolation transformer, there is another audio transformer too, which will change the output voltage level depending on the input AC signal. The loudspeaker is a huge load and needs to provide the required current and voltage across it to produce proper sound vibration. An audio transformer with setup feature will set up the voltage or the current level to drive a load across it. Same happens for the step down transformer too. It converts the voltage from higher to lower with the increased current output. The audio transformer also provide impedance matching specifications. When the output of one circuit or device is directly connected to the input of another device, it is very important that the device output impedance and device input impedance both are matched. An impedance matching transformer provides this feature and converts higher impedance output to lower impedance to drive a low impedance speaker or feeding to another low impedance device. Working of an audio transformer and its construction. Although an audio transformer does not have a physical connection between his primary and secondary coil, the transformer provides bidirectional feature between these two windings. We can also use the same primary side as secondary and secondary as primary. In such case, the transformer provides signal loss in one direction and signal again in reverse direction or vice versa. The audio transformer works at frequencies between 20 Hz to 20 kHz, so the operation of an audio transformer has much wider frequency range. As discussed above, the audio frequency transformer uses impedance balancing technique. It is very useful for balancing amplifiers and loads that use different input or output impedances for maximum power transfer application. In modern days, speaker impedance ranges from 4 to 16 ohms. Typically, 4 ohms, 8 ohms, or 16 ohm speakers are available, whereas transistors or solid state amplifiers use 200 to 300 ohms output impedance. If the amplifier is a retro design, such as old valve or tube amplifier, then the output voltage sometimes reaches 300 volt with 3k impedance. So, we need impedance matching transformers which will convert the high impedance to low impedance and should convert the voltage and current to a level which will directly drive the loudspeaker. A transformer can have multiple windings in the primary and the secondary side. The ratio between primary and the secondary windings, the number of coil turns in the primary side NP and a number of coils turns in the secondary NS is called the turns ratio. This turns ratio also defines the primary and secondary voltage ratio, as the voltage is directly proportional to the primary and secondary winding turns. Audio transformers often perform several functions at once. Where used, they allow the AC audio signal to reach the loudspeaker, which prevent any DC from the amplifier affecting the operation of the loudspeaker. They also provide an isolated external connection for the loudspeaker, improving safety. They can match the low input impedance of the loudspeaker, typically in few ohms, to the much higher output impedance of an amplifier, allowing maximum power to be transferred from the amplifier to the speaker. So this is all about transformers. So thanks for watching. Please subscribe to this channel and stay tuned for more videos. Thank you.